Hello, we are now going to talk a little more about separation of variables, separable equations, in the context of implicit solutions of ordinary differential equations. So let's consider, remember that here implicit solutions should come to no surprise, since we have learned something that we call implicit differentiation. Okay, so there are expressions that relate variables. However, it's not possible to express one variable explicitly as a function of the other variable, but they are related, they are bound by this implicit relationship, and therefore we had learned back in calculus 1 how to differentiate those type of relationships. So let's consider a differential equation of the form, say, y prime equals xy over y squared plus 1. So we're going to consider this y prime as a derivative of y with respect to x, and that expression we're going to rewrite as a product of x times y over y squared plus 1. Okay, so we want to think of this right-hand side of the differential equation as an expression here that looks like a function we call here g of y multiplying another function we call f of x. So the right-hand side is being expressed here as a product of two functions, one in terms of x and one in terms of y. So what we really like to do is to proceed in solving this differential equation by separating the variables. So we can write the left-hand side of the differential equation in terms of y, and then we can write the right-hand side in terms of x, and therefore we would have this expression. So y squared plus 1 over y times dy equals x times dx, and by doing so we are keeping these variables separate in both sides of the equal sign. So the left hand side we can simplify algebraically a little bit and express it as y plus 1 over y, but really interested on integrating in both sides of this expression. So the left hand side becomes y squared plus natural log of absolute value of y. The right hand side, I'm going to write here the constant of integration c plus x squared divided by 2. Now, it is not possible to solve for y in terms of x, and that is something that we can see. So on the left hand side we have a square of y, and we also have a natural log. So if we solve, well, this is simply, it's not possible, right? So if we solve for one by taking exponential, then the other y squared gets trapped. If we take square roots, then there's still you wouldn't be able to solve. But what we can do is we can customize this a little bit. One thing I must note is that I'm missing a term here. This should be just like the x squared over 2. This y squared is also divided by 2. So we could do an extra step. We could multiply both sides of this equation by 2, and so we have something like y squared plus 2 times natural log of absolute value of y plus 2c plus x squared. So we can call this term d, this constant 2 times c, we can call that a constant d. And so we can rewrite the expression as y squared plus 2 times natural log of absolute value of y plus a constant d plus x squared. This is the solution. This is the solution in implicit form. In fact, we would say that this expression is the implicit solution to the ordinary differential equation. And so what we can do next is to verify that indeed this implicit solution satisfies the differential equation. So we start with the implicit solution, and let's differentiate in both sides. Differentiate in both sides of this equation. Okay, we're differentiating with respect to x. Take the derivative with respect to x, and so this becomes 2y times dy dx plus 2 times 1 over y times the derivative of y. That's on the left-hand side, and then the right-hand side we have derivative of a constant, that'll be 0 plus 2x. So we can factor dy dx on the left-hand side. In fact, we can factor 2 times the derivative of y, and that leaves us with y plus 1 over y on the left-hand side, and then the right-hand side is 2 times x. So it's easy to see that we can divide by 2 in both sides here, and then we can solve algebraically for dy dx. So we started with the implicit solution, differentiating both sides. We have dy dx, we can do some algebra here and come up with a common factor. And so the left-hand side can easily be solved in terms of x and y on the right-hand side, right? And so with an additional step, we can rewrite the denominator, and actually 2 additional steps, then the denominator can be expressed as y squared plus 1, while the numerator here becomes x times y, which is exactly what we needed, right? Because if we remember the origin of this, the original formulation was, this is the original formulation, and we had the derivative equals to this expression xy over quantity y squared plus 1. So this is the original formulation, and this was a verification of the implicit solution, right? And so they check. They are exactly, the original differential equation is satisfied